Hey guys, what's up? So in this video, we will tackle all about thermal stress. We will discuss to you from its definition as well as its applications in real situations. We will learn how to solve this kind of problem and know where did this equation came from. We will provide some problems as examples to solve using this derived equation. Moreover, some prototypes will be shown in this video for convenience to visualize the effects of this kind of strain. So let's start. So what exactly is thermal stress? So when the applied force is in the form of temperature, the resultant stress is called thermal stress. It is observed when an object expands or contracts due to the change in temperature. Thermal stress is measured using feet or meters, and the effect of temperature on conductors is vital. In heating, the thermal conductors expand, while in cooling, the thermal conductors contract. Thermal stress can be destructive, such as when expanding gasoline ruptures a tank. However, it can also be useful. For example, when two parts are joined together by heating one in manufacturing, then slipping it over the other and allowing the combination to cool. In simple words, thermal stress is a stress caused due to the change in temperature. And now, let us proceed to the applications of thermal stress.
Hey there, I see you're done hearing about the definition about thermal stress. Let's move on to the applications now, shall we? So, the applications of thermal stress. You're probably wondering right now, where can I use the things that I've learned on thermal stress in my day-to-day lives, or projects that I may take up on in the future? Now, due to the tendency of objects expanding or contracting depending on the temperature, thermal stress can be used in a wide variety of ways. Such things are shown in the examples to follow. Now, first example. You see those electrical posts? Their wires are sagging. Now, this is not a mistake, but a clever way to tackle the problem the electrical posts face in winter. When comes winter or the cold season, the wires tend to compress. Now, if not left with some leeway, they break when they compress. So engineers gave leeway to the wires they install on electrical posts so that they may not break come cold season. Next up is railway tracks. Now, railway tracks have posed a major problem to people in the past due to their tendency to expand in the summer and making the tracks deform due to them expanding. Now, to tackle this problem, the engineers have left gaps when installing the railway tracks so that when the metals in the tracks expand, they just fill in the gaps, preventing deformations to occur. Now, next up is an ingenious way of using materials with the help of thermal stress. Now you see that iron rim on a wooden wheel. Now, would you believe me when I say that before installing that iron rim on the wooden wheel, the iron rim was much smaller than the wooden wheel? Now, they used the expanding and contracting of the iron rim to their advantage. Now, they heat up the iron rim so that when it expands, it may fit perfectly on the wooden wheel, or sometimes there's still some leeway. Now, after that, they cool it down so that it compresses back to its original size. But with it already on the wooden wheel, it compresses on the wooden wheel, making it a firm fit on the wooden wheel so that it will not separate from it. Now, isn't that ingenious? They saved iron from making a bigger iron rim, and also they use the thermal stress in such a fascinating way. Now, to learn more about thermal stress, up next is the derivation of equations. Look forward to it.
There are concepts that we need to know in order to understand and solve the problems that deals with thermal stresses. First, when temperature increases, it will produce positive strain which results elongation or expansion. While if the temperature decreases, it will produce negative strain, mo nang naay contraction. Kani nga deformation is isotropic, which means equal siya sa every direction and also proportional to the change in temperature. That's why we can equate thermal strain as epsilon T is equal to the alpha, which is the value of coefficient of thermal expansion, multiplied to the delta T, which is the temperature change. If the temperature change is uniform throughout the body, which it also means that thermal strain is also uniform. Since strain is equal to the deformation T or change in T per the value of any dimension L, deformation T is equal to the strain multiplied to the value of L, which we can also expand to alpha times the delta T times L. Forces that result from temperature changes are statically indeterminate, which means ang forces dili ma-determine using equilibrium analysis lang. That is why we derive compatibility equations to provide us additional equations na kailangan to solve a problem, but also with the inclusion of thermal expansion para ma-analyze ang deformation. So the first thing to do is relax the supports. Tangtangon na to ang mga supports like fixed supports or walls na gapugong sa iya to deform, and then show the body or the material deforming freely. Second, since naka-deform na ang body, ato dayong ibalik ang support, and then we apply necessary forces that opposes to the elongation or contraction para ma-attach balik sa support if mabinat or ma-contract. Lastly, we then write the relationships between the thermal expansion and the deformations due to the force na gi-apply para mabalik sa iyang original position.
Problem number 1. Calculate the increase in stress in each segment of the compound bar if the temperature is increased by 80 degrees Fahrenheit. Assume that the supports are unyielding and use the following data. The given, the aluminum has an area of 1.5 inch squared and modulus of elasticity is 10 times 10 to the power of 6 psi, and the coefficient of thermal expansion per degree Fahrenheit is equal to 12.8 times 10 to the power of negative 6 per degree Fahrenheit. And the steel having an area of 2 inches squared and elasticity of 29 times 10 to the power of 6 psi and having a coefficient of thermal expansion per degree Fahrenheit of 6.5 times 10 to the power of negative 6 per degree Fahrenheit. So here is our free body diagram or FBD. Let's remove the constraints here. So supposedly these bars, aluminum and steel, will expand due to the increase of temperature by 80 degrees Fahrenheit. So this is the thermal deformation of aluminum, and this is the thermal deformation of steel. Assume that the supports are unyielding. Unyielding, it means these bars mubalik ra siya sa iyang normal position due to its internal forces. So, internal forces of aluminum, P sub aluminum. So, in this area is the normal deformation of aluminum. Also, in the steel, this is its internal force. And in this area is the normal deformation of the steel. So we have our free body diagram or the FBD. So in this free body diagram, we can see our equation, which is the thermal deformation of the aluminum plus the thermal deformation of the steel is equal to the normal deformation of the aluminum plus the normal deformation of the steel. So note that the deformation is equal to the stress multiplied to the length over the modulus of elasticity, or also equal to the pressure or stress multiplied to the length over the area times the modulus of elasticity. And the thermal deformation is equal to the thermal expansion times the change of temperature times the length. So this equation ato i-substitute diri nga equation. So now let's substitute the given constant to the variables. So we have the thermal expansion of the aluminum, which is 12.8 times 10 to the power of -6, and the change of temperature 80 degrees Fahrenheit times the length of the aluminum, which is 10, plus the thermal expansion of the steel, which is 6.5 times 10 to the power of -6, and times the change of temperature, which is 80 degrees Fahrenheit, times the length of the steel, which is 15, equals to the P aluminum times the length of aluminum, which is 10, over the area of aluminum, which is 1.5, times the modulus of elasticity of aluminum, which is 10 times 10 to the power of 6, plus P steel times the length of the steel, which is 15, over the area of the steel, which is 2, times the modulus of elasticity of the steel, which is 29 times 10 to the power of 6. If we calculate this, we will get 0.01804 equals to the P aluminum times 6.667 times 10 to the power of -7, plus P steel times 2.568 times 10 to the power of -7. So this 2.568 times 10 to the power of -7, ato ni siya i-distribute diri. So we will have, we will divide this number to these components. Okay, so we will have 69,760.247 equal to the P aluminum times 2.578 plus PS steel. So this will be our first equation. So mangita na sa taglain nga equation diri sa atong free body diagram. So as we can see in our free body diagram, P aluminum and P steel is equivalent forces. Diba? These are the stresses that will push back the aluminum and steel to their original position. So P aluminum is equal to P steel. Okay, P aluminum is equal to P steel. So in this case, we can write them as P. So going back to the first equation, 69,760.247 is equal to the P aluminum, ito gibot niyan P, times 2.578 plus P steel, which is also P. So let's find P, calculate for P. So P is equal to 19,496.995 pounds divided by 1,000 para may mug kips. So P is equal to 19.497 kips. So ang gipangita man nato is calculate for the stresses. So stress of aluminum is equal to the pressure over the area of aluminum. So pressure is equal to 19.497 kips over the area of aluminum is 1.5. So the stress of the aluminum in the aluminum is equal to 12.998 KSI. So on the steel, so we have the same solution, same formula. So the stress of steel is equal to the pressure over the area of the steel, which is 19.497 kips over the area of the steel, which is 2, equal to 9.749 KSI. And that's all.
If a rod of 1025 steel of 1 meter long is heated from 20 degrees to 80 degrees Celsius while its ends are maintained rigid, determine the type and magnitude of the stress that develops. Assume that at 20 degrees Celsius, the rod is stress-free. Use alpha equals 11.7 times 10 raised to the power of negative 6 per degree Celsius and E equals 200 gigapascal. For question letter B, what is the stress magnitude if a rod of 0.5 meter long is used?
If we are asked to calculate for the magnitude and type of stress, let's recall that stress is equal to modulus times strain. But we can account for strain because we know that thermal expansion is going to make this rod extend. Normally, we think of strain as LF minus LI all divided by LI. But in this case, we're gonna write this in terms of thermal expansion coefficient. So, thermal stress is equal to modulus times thermal expansion coefficient times the change of temperature. Get thermal stress is equal to modulus times the thermal expansion coefficient times the change of temperature. Now, usually we take the change of temperature as final minus initial. But now, if we need or we want to know the exact and correct sign convention, we need to take T naught minus T final. Using the data given and substituting it to our formula, we get thermal stress is equal to 200 times 10 raised to the power of 3 megapascal multiplied by 11.7 times 10 raised to the power of negative 6 per degree Celsius and multiplying it by 20 degrees Celsius minus 80 degrees Celsius, and then by calculating it, we get negative 40.4 megapascal, and that it is undergoing through compression. Which makes sense because as this rod is heated up, it wants to expand, but we're not allowing it to expand and we are restricting it from expanding, so it's giving into a state of compression.
In this problem, we are given a new length, but as you notice on the previous problem, we didn't even use the length because it doesn't come into place. Since strain is equal to final length minus initial length all over initial length, sure enough that if we start with a longer rod, then we can think that it is turned off, but in fact, the final length is also turned off. Therefore, it has the same answer as part A.
Have you ever shattered a glass when you pour boiling water on it? Or have you ever seen cracks from a wall? I bet you have experienced seeing this kind of situation. But the question is, how did those things happen? As we all know, once a material is subjected into heat or cold, it will experience or it will undergo expansion or contraction. In some cases, there will be a restriction or there will be an opposing force that won't allow the body to expand nor contract, resulting to thermal stress. So to make things more clear, this is the model that we created out of the given problem. So as what you can observe, this pipe right here is in between these two wooden posts. So what do you think will happen if this pipe right here is subjected into heat or cold? So basically, this material right here will undergo expansion or contraction. Since there's an opposing force right here, there will be a restriction in which there will be an opposing force that won't allow the body to expand nor contract, resulting to thermal stress. In civil engineering, thermal stress can have a significant impact to the structure or to its design. Once the stress exceeds the strength properties of the material, it will no longer hold the pressure and will probably lead to breakdown in some parts. This error jeopardizes the overall shape or overall design of the structure, resulting to instability, deformity, or even hazard. That's why civil engineering always take into account thermal stress.
Before we end this lecture video, let's have a quick summary and few add-ups. We all know that thermal strains are strains that develop when a material is heated or cooled. This means that this happens when there is a rapid increase or decrease in temperature, which then causes the body to expand or contract. So if temperature deformation is permitted to occur freely, no load or stress will be induced in the structure. In some cases where temperature deformation is not permitted, an internal stress is created, which is also known as thermal stress. Meaning, if the deformation is unrestricted, mag-elongate continuously ang object since wala may restrictions nga mag-limit sa iyaha nga mag-elongate. So, there will be no thermal stress, only thermal strain. Partially restricted, if ang deformation is partially restricted, so since na may wall or barrier na mag-restrict sa iyaha nga mag-elongate further, then it will have a limited elongation. And para mabalik siya sa original position, there will be an internal stress which termed as thermal stress. So, in partially restricted, there will be thermal stress as well as thermal strain. So, if ang deformation naman kay totally restricted, walay thermal strain since maka-elongate ang object since dili maka-elongate ang object tungod kay naamay ga-restrict sa iyahap sa pag-elongate. So, no elongation, no thermal strain. Pero naa siya thermal stress because naay internal force nga ga-act atong object. Okay. Moving on, let's have the equations that can be used in problems related to thermal strain and stress. So to solve for the amount of deformation due to change in temperature, this is given by the deformation due to change in temperature, which is equal to the coefficient of the thermal expansion times the delta T, which is the difference in or the change in temperature times length. And to solve for the deformation due to equivalent axial stress, this is given by the deformation due to load, which is also equal to P, which is the force or the load or the pressure times length all over area times E, which is the modulus of elasticity, which is also equal to stress times length times modulus of elasticity. So these two equations are the general equations that will be used in solving thermal strain problems. On the other hand, applications of thermal strain to everyday life are evident in different structures. So this includes electric wires in posts, railways gaps, wheels on iron rings. But it does not limit only to those structures. Thermal strain is also evident specifically to expansion joints, thermostats in temperatures, I mean thermostats in thermometers, engine coolant, and etc. Also, sa balay, the concept of thermal stress and strains can also be observed. Like, the concept has like kanang pag-chismis sa mga chismosa, it is an unrestricted elongation. Ngano? Kay why honong storya 24/7. Walay undang, walay limitations, and ilang storya kay unrestricted deformation like gasigi lang nga gasigi. So, other pod kay sa balay, kanang kibali pagkasabaan ka kay naglaag ka tas may pananghid, nagyaw-yaw na si mama ug si papa, tas ikaw ni bukade mong baba kay lagi gusto ka mo defend sa imong self. Pero naay thermal stress nga nag-restore sa imong jaw from its original position kay kabalo ka nga mali ang pagtubag-tubag. So and that is the partially restricted deformation. Kay limited o tungod sa katon, limited lang ang pag-elongate sa imong baba. Og kana pong kuan, mawala ang internet connection ang inyong Wi-Fi. So mag-open ka og Google. And walay elongation sa bar sa ubos sa search button kay wala siya ga-move kay lagi wala kay internet. And that is totally restricted, wala nag-elongate. So and that wraps up our report. We are hoping that you all understood everything about thermal stress and thermal strain at this moment of this lecture video. Keep safe and thank you for spending your time with us. Adios!